In Part 2 of the General Performance Principles Takeoff lesson, you learnt about some of the factors that affect the takeoff, namely the aircraft mass, the air density, and the wind. Part 3 continues with the factors that affect the takeoff, and it starts with the effect of runway slope. The next factor that can affect the takeoff performance is the slope of the runway. Slope has an impact on the takeoff distance because of its effect on how the component of weight acts along the longitudinal axis of the aeroplane. Notice here that a stationary aircraft on a level runway has its weight acting straight downwards towards the center of the earth. However, when the aircraft is on an upslope, although the weight still acts towards the center of the earth, there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will reduce the acceleration of the aeroplane and therefore increase the takeoff distance. Conversely, when the aeroplane is on a downslope, the weight component now acts in the direction of thrust. This adds to the forward force, therefore it will increase the acceleration and decrease the takeoff distance. A rough calculation to help quickly quantify the effect of slope is to assume that for every 1% slope, the takeoff distance is affected by 5%, or by a factor of 1.05. A general rule for airports within the United Kingdom, there is a restriction for up to 2% slope, and most takeoff performance calculations will account for slopes only up to 2%. If, however, the runway has a slope in excess of this, then permission will need to be given by the authority for the aerodrome to operate, and the pilot will also need to demonstrate competency in using it. The slope at some airfields, particularly around southern Europe, permit takeoff and landing in only one direction. Treat these runways with extra caution and always check that the current wind velocity will still allow a safe takeoff. You can check with the aerodrome information charts about the runway slopes, such as the one shown on screen. Most takeoff graphs assume a paved, hard surface. If the condition of the runway is not like this, then the effect on the takeoff distance needs to be understood and corrections have to be applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels. This drag will reduce the aeroplane's acceleration and, as a result, increase the takeoff distance. Most takeoffs and landings that you will encounter throughout your professional career will undoubtedly be on hard, paved runways. However, these surfaces, as well as grass surfaces, may be covered by standing water, snow, slush, or ice. These contaminants may cause significant performance loss to the extent that a safe takeoff is not possible. Standing water, snow, and slush behave in a similar manner to the effect of grass in that they create additional drag as the wheels pass through them. But they also create additional drag as the spray from these substances impinges on the aeroplane. This is known as impingement drag. The greater the thickness of these substances, the greater the impingement drag, and therefore the greater the increase in the takeoff distance. In fact, there may be so much contamination on the runway that the acceleration of the aeroplane is insufficient to safely get it airborne before the runway runs out. There is potentially an even greater effect on the aeroplane from ice, water, and slush on the runway, other than the effect of the increased drag on the wheels. These substances will dramatically reduce the friction between the wheel and the runway, acting similarly to a lubricant. Whilst this may not seem too much of an issue whilst trying to get airborne, it does present an enormous problem when trying to abandon the takeoff and bring the aeroplane to a stop before the end of the runway. Because there is very little friction between the wheel and the runway surface, the wheel cannot be retarded efficiently by the brakes, otherwise the wheel will lock, and the wheel friction with the runway will reduce even further. This is most obvious when ice is present on the runway. This part of the lesson is interactive, and it will help you to understand the relationship between the various types of contaminants, the braking effect with these contaminants, and the effect on the stopping distance. The aeroplane you see is traveling from left to right. On the right-hand side of the screen, you can select the type of surface you want to test, either dry, wet, or icy. Once you have done so, looking to the left-hand side of the screen, move the slider on the horizontal bar which is positioned underneath the 3 gauges. Moving the slider to the right increases the applied braking force. But be careful. Too much braking force will cause the wheels to lock and reduce the braking efficiency. The maximum amount of braking force you can apply will change depending on the runway contamination. When you have completed this section, just click on the forward arrow to continue with the rest of the lesson. There are other effects which runway contaminants can have on aeroplane performance, which include the possibility of a power unit failure due to water ingestion, directional control problems, and possible structural damage. It is therefore vital that the pilot be aware of the type of runway contamination, its depth, its extent, its effect on the braking, and of course its overall effect on the operation concerned. The recommendation by the United Kingdom CAA is that takeoff should not be attempted when the depth of water, wet snow, or slush is more than 15 millimeters. But check with the aeroplane flight manual in case it has a more severe restriction. The information on the contamination will be provided by the aerodrome and issued to the pilot through a report. These reports are either by SNOTAM or a runway state code. Use these reports and your aeroplane flight manual to best gauge the performance considerations. An important point to note is that there is a distinction between damp, wet, and contaminated runways. A runway is considered to be damp when there is moisture present on the surface which changes its color, but insufficient moisture to produce a reflective surface. A wet runway is one whose moisture level makes the runway appear reflective, but there are no areas of standing water in excess of 3 millimeters deep. A contaminated runway is one when there is more than 25% of the runway covered in a layer of moisture whose specific gravity is equivalent to a depth of 3 millimeters or more of water. The importance of runway contamination cannot be stressed enough, as many fatal accidents may have been avoided had due account been taken of the situation. Shown on screen is a button which you can click, which will open up a document produced by the UK CAA. This discusses the issues regarding the operations on contaminated runways. It is highly advisable you read through this safety document and fully absorb the information it contains. The next factor that can affect the takeoff performance is contamination of the airframe. This includes the effect of airframe ice and excess water. Airframe ice will accumulate as a result of icing conditions being present at the aerodrome. These conditions could have resulted from a frost, freezing precipitation, or from a snowfall. The effect of these contaminants can be significant if they are not properly removed. The first effect that they have is to disrupt the airflow over the wing. This results in an increase in drag, but, just as importantly, a reduction in the lift force. The second effect is that the contaminants will increase the weight of the aeroplane, and therefore increase the stall speed. The combination of these effects is such that the takeoff distance required will dramatically increase. Icing conditions can also lead to the jamming of the control surfaces and blockage of important instruments. So it is vital that a proper pre-flight inspection be carried out, and then subsequently the correct method of ice removal is carried out. It is compulsory by law to ensure that all aeroplanes are free from ice and free from any contamination at the commencement of takeoff. It may seem strange, but excess water on the aeroplane can lead to the same effects that ice has. In heavy rain, research has shown that lift can be reduced by as much as 30%, and drag increased by as much as 25%. This, combined with increased aircraft weight, can create a significant performance loss, and thus takeoff in heavy rain really should be avoided. Unfortunately, this advice is too often ignored. Heavy rain is usually accompanied by other potential fatal hazards. These include decreased visibility, wind shear, and microbursts. Wind shear occurs when there is a rapid change in wind speed and direction. If this occurs when the aeroplane is at or near the ground with low forward speed, then there is a considerable chance that the aeroplane will become uncontrollable and may even stall. Takeoff, when wind shear is observed or forecast, should be avoided. A microburst is a column of air descending very rapidly at speeds of up to 250 km per hour, which, upon impact with the ground, spreads out in all directions. The descending column of air may or may not be accompanied by rain. The microburst is the single most hazardous weather phenomena to aeroplanes close to the ground, when they are either in the takeoff or landing phase of flight. The microburst was only first understood in the late 1970s and, after the crash of the Delta Airlines aeroplane that killed 137 people on August 2, 1985 at Dallas-Fort Worth, significant changes in safety procedures were put in place to reduce this hazard. There is a saying amongst pilot instructors that it is far better being down here and wishing you were up there than being up there and wishing you were down here. Time pressure, passenger pressure, and commercial pressure cannot and should never come in the way of safety. Delay the takeoff if necessary, and wait for the weather to improve. The last factor to consider that affects the takeoff is the configuration of the aeroplane in terms of the flap setting. Flaps are trailing edge devices used to increase the camber of the wing and generate more lift, thereby reducing the takeoff speed. However, the use of a lot of flap will dramatically increase drag as well. Let's take a look at how different flap angles can affect the takeoff distance. With no flap, the aircraft will accelerate and then climb to the screen height, as shown. However, with some flap selected, more lift will be generated, and the aircraft will get airborne at a slower speed. This can be by as much as 10 knots. However, with flap, a small penalty is paid by the fact that the initial climb angle is shallower. Nevertheless, the overall effect is that the takeoff distance reduces. If too much flap is used, then the wing will generate more drag than lift. The result of generating more drag than lift is that the acceleration is reduced and the takeoff distance is increased compared to the acceleration achieved on a no-flap takeoff. Too much flap would also significantly reduce the angle of the initial climb and exacerbating the effect. Because of the effect of large flap angles on the takeoff distance, most aeroplanes are restricted to certain flap settings on the takeoff. For example, the 737-400 series only has 2 flap settings for takeoff, either 5 or 15 degrees. As a simple rule, increasing the takeoff flap setting will improve your takeoff performance, but it will decrease your climb performance. Familiarize yourself with your aircraft and use the flap settings laid down by the manufacturer in the aircraft manual. This completes the lesson on takeoff performance. In this lesson, you should have learnt and understood all the components affecting the takeoff, and more importantly, what determines the takeoff performance. Learn the capabilities of your aeroplane and never attempt to exceed them. Never fall prey to time pressures, which make you cut corners. Most aeroplane accidents happen in either takeoff or landing phases of flight, so always prepare for the worst. The next lesson will deal with the performance of an aeroplane in the climb.